We are next going to talk about how we can use the ANOVA framework to study the effects of multiple independent variables. All other tests we have studied so far have studied just one variable or one factor at a time. Now we are going to move to talking about two or more independent variables. These variables are also called factors, and that is why this type of ANOVA is called Factorial ANOVA. Even though we are studying multiple independent variables, we are still only studying one dependent variable. At this point, all of our dependent variables have been continuous, measured on the interval or ratio scale of measurement, and that's going to continue to be true with Factorial ANOVA. Our independent variables will continue to be categorical, measured on the nominal scale of measurement. I'm going to illustrate Factorial ANOVA using an example from some of my recent research. In this study, we walked around a college campus and approached people who were standing around in pairs of two. We carried with us a tray that had two kinds of tasty treats on it, chocolate drizzled strawberries or chocolate-covered Oreo cream cheese truffles. We asked one person to be a taste tester and the other to be an observer. In this way, we created a condition of role, actor or observer. The actor made a food choice, strawberry or truffle, and then tried the food. This created another factor, strawberry or cookie truffle. Because we had two variables that each had two levels, this design has 4 total cells or combinations of conditions. In any factorial design, the total number of cells, groups, or conditions is always the number of levels in one variable multiplied by the number of levels in the other variable. We've talked about the independent variables in this study, role and food, but we haven't talked about the dependent variable yet. So after the taste tester or the actor chose and tried the food, we asked all participants to indicate how much they agreed with this statement. They agreed with the statement either I am or my friend is committed to maintaining a healthy weight. So we wanted to see if actors and observers would perceive the taste tester's goal commitment differently depending on what food they chose. Here are the observed findings from our study. Factorial designs allow us to test differences in these numbers in multiple ways. We can test both main effects and interactions. Main effects are the average difference between conditions of one variable while collapsing across levels of the other. Interactions are how the levels of both variables combine to additionally explain variance in the dependent variable. When examining for main effects, we are asking about effects of only one variable at a time. So we want to average the cell means of all the variables that share that same level. Let's say we are interested in the main effect of role. Did actors and observers differ? We need to ask whether all the people who shared the actor level differed from all the people who shared the observer level. We are effectively comparing the average of the two boxes with the actor role to the average of the two boxes with the observer role. Assuming equal cell sizes, we can just average these two numbers that share level of role. I've created these means and I've rounded to the thousandth decimal place so you don't get blinded by any of the rounding stuff. So the test of the main effect of role evaluates whether 6.125 is different from 6.305. We are in essence comparing 6.14 and 6.11 combined versus 6.83 and 5.78 combined. You'll notice I'm going to work really hard to use the word versus when I am talking about comparisons. That is because it's really easy to say something like comparing apples and oranges, but that language is confusing when you're trying to compare or combine. So please do a similar job yourself and focus on using the word and when you are combining groups and the word versus when you are comparing groups. Okay, back to our task at hand. We can also test the main effect of food. Did perceived commitment differ based on which food the taste tester chose? Here we want to compare all of the cases where the taste tester chose the strawberry compared to all the cases where the taste tester chose the cookie truffle. So here we compare the means of the two cells involved, 6.485 versus 5.945. Or we could say 6.14 and 6.83 versus 6.11 and 5.78. Main effects compare across levels, like strawberry versus cookie, while ignoring the other variable. Instead of comparing two averages, with an interaction, we are going to compare comparisons. Every interaction is made up of at least two simple effects. Let's contrast simple effects with main effects. When we examined the main effect of food, we compared 6.485 versus 5.945. These numbers represent the means of cells, and we compared them because they differed in level of food. A simple effect is a comparison of just two numbers or two cells. Think like a contrast test. We find just two cell means and we compare them to each other. For instance, we could examine the simple effect of food among actors. Here we are not averaging 6.14 and 6.11. Instead, we are going to compare them. When you only have two numbers, you can think about this comparison as a difference score. 6.14 minus 6.11 equals 0.03. This simple effect is 1/2 of an interaction. In order to complete the interaction, you have to compare this simple effect to its parallel simple effect. The parallel or the complementary simple effect is to compare the effect of food, strawberry versus cookie, among the observers. So to compare 6.83 versus 5.78. Subtracting one from the other gives us a difference of 1.05. The actual interaction is a test of whether these comparisons are different. Are the differences different? So we would compare 0.03 versus 1.05. Are those numbers different? Yes. Let's look back to our data to see how this works. Among the actors, perceived commitment is a little higher when the taste tester chose the strawberry than the cookie. There is a very small positive effect of food. But this looks really different among observers, because among observers, perceived commitment is much higher when the taste tester chose the strawberry than when they chose the cookie. There is a very large positive effect of food for observers. Now we can also reframe this interaction by talking about the simple effects of role at each level of food. The effect of role among when the food was strawberries would be 6.14 minus 6.83, which equals negative 0.69. That's a moderate negative effect. The complementary simple effect here would be the effect of role when the food was the cookie truffle, so 6.11 minus 5.78. The interaction tests the difference between these simple effects. It compares negative 0.69 to positive 0.33. Each of these ways of thinking about the interaction is statistically identical. That means the simple effects, no matter how you frame them, are going to be the same. Do the math behind these comparisons, and you will see how they are equal. Negative 0.69 minus 0.33 is the same as 0.03 minus 1.05. Instead of thinking about the data using numbers in a table, we can also start to think about relative differences as they might be shown on a figure. You'll notice here that I'm using a bar chart instead of a line chart. Chances are that in past classes, you've learned about interactions with a line chart, and you've been taught that if the lines cross, then there's an interaction. Technically speaking, that's correct, but it's also misleading. Because our designs have categorical independent variables, the bar chart is actually more appropriate for our data. So let's use this figure to understand our interaction between role and food on perceived commitment. I'm going to give each cell, which is represented by one bar, a letter for comparison. So here we can compare the simple effect of role among food by comparing A versus B to C versus D. So A versus B versus C versus D. And we can compare the interaction through the simple effects of food among role. So A versus C versus B versus D. To wrap up, remember that an interaction is a pair of simple effects. If these simple effects are different from each other, then there is a statistically significant interaction. Visually, you can see here that the differences are different from each other. Practically, this means that we cannot accurately describe our data by talking about main effects alone. Yes, in this case, there's a main effect of food. When the taste tester chose strawberries, perceived commitment was higher. Remember 6.485 versus 5.945? But that's really not the full story. It's actually the case that choosing the strawberry led to perceived commitment only among the observers. Among the actors, there was actually no meaningful difference between strawberries versus cookies. To tell the real story of our data, we have to report the interaction and the simple effects. Statistically speaking, what this means is that the effect of one variable depends on the level of the other. In our example, the effect of food, whether the effect was small or big, depended on the role our participants were playing.